Beneath the quiet neighborhoods stretching across Hollister, Pleasanton, and Dublin, the landscape is shifting in a way that is both subtle and deeply consequential. Streets that appear still to the eye are, in fact, inching sideways year after year. Sidewalks no longer align as they once did. Fences tilt, curbs fracture, and slowly drift apart. The changes are so gradual that they can pass unnoticed in a single moment, yet undeniable over decades. What kind of fault moves without announcing itself through constant violent shaking? Why does it slip quietly in some places, only to store energy in others? And how can a fault that seems almost gentle still carry the potential for powerful earthquakes? The structure responsible is the Calaveras fault, a major branch of the broader San Andreas fault system. It runs for roughly 76 miles, or about 122 kilometers, cutting through the eastern side of the San Francisco Bay Area in a northwest to southeast direction. Though often overshadowed by its more famous neighbor, its behavior is far from secondary. It is one of the most active faults in California, defined not only by its seismic history, but by the unusual way it releases stress. The region it occupies is part of a vast transform boundary between the Pacific Plate and the North American Plate. These two enormous sections of Earth's crust are not colliding or pulling apart, but instead sliding past one another. The Pacific Plate moves northwest at a rate of approximately 2 to 3 inches per year, equivalent to about 5 to 7 centimeters annually, while the North American Plate shifts more slowly in a west-southwest direction. This lateral motion produces what geologists classify as right lateral strike-slip faults, meaning that if a person stands on one side of the fault, the opposite side appears to move to the right. Within this system, the Calaveras fault serves as one of many interconnected strands that share the burden of accommodating tectonic movement. The region is not governed by a single fracture, but by a network of faults that divide and redistribute strain. This complexity is part of what makes the area difficult to fully predict. Stress does not accumulate evenly, nor is it released in a uniform way. What distinguishes the Calaveras fault from many others is a phenomenon known as seismic creep. Unlike locked faults that remain stuck for long periods before releasing energy in sudden earthquakes, creeping faults move slowly and continuously near the surface. This motion does not typically produce noticeable shaking, yet it steadily alters the landscape. In Hollister, the effects are visible in ways that require no specialized instruments to detect. Roads that were once straight now display subtle bends. Concrete sidewalks have shifted inches out of alignment. Over the course of decades, entire sections of infrastructure have been displaced. Measurements taken along certain streets indicate that since the early 20th century, the ground has moved more than 2 feet, or roughly 65 centimeters. That translates to an average creep rate of about 1/4 of an inch per year, or around 6 to 7 millimeters annually in some areas. This slow, persistent motion raises an important question. If the fault is constantly releasing energy, does that reduce the likelihood of a major earthquake? The answer is not straightforward. While creep does relieve some stress, it does not eliminate it entirely. The upper portions of the fault may slide gradually, but deeper sections can remain locked. Over time, these deeper zones accumulate strain, which can eventually be released in sudden, more powerful seismic events. The physical conditions within the fault zone help explain why creep occurs. One key factor is the presence of a rock known as serpentinite, formed through the alteration of magnesium-rich rocks such as basalt and gabbro when exposed to heat and water. This transformation process produces a material with low frictional strength. In simple terms, it is relatively slippery compared to surrounding rock types. When a fault cuts through such material, it can move more easily without becoming tightly locked. Another contributing factor lies in the pressure of fluids trapped within the rock. Deep underground, tiny cracks and pores are often filled with water or other fluids. When pressure builds within these spaces, it pushes outward against the surrounding rock surfaces, effectively reducing friction. This increased pore pressure acts almost like a lubricant, allowing sections of the fault to slide more readily. Together, these conditions create an environment where parts of the Calaveras fault can move steadily without generating significant earthquakes. Yet this behavior is not uniform along its entire length or depth. Some segments creep more actively than others, while deeper sections may remain resistant to motion. This uneven distribution of movement adds to the uncertainty surrounding the fault's long-term behavior. Historically, the Calaveras fault has demonstrated its capacity for more than quiet motion. Since the mid-19th century, it has produced multiple earthquakes with magnitudes of 6 or greater. These events, while not as large as the most extreme earthquakes associated with the San Andreas Fault, are still capable of causing significant damage. Structures not designed to withstand seismic forces can suffer severe impacts even from moderate shaking. One of the more notable events occurred in the 1980s near the town of Morgan Hill, where a magnitude 6.2 earthquake caused injuries and widespread structural damage. The event served as a reminder that even faults known for creeping behavior can generate sudden and disruptive seismic activity. In recent years, patterns of smaller earthquakes along the fault have drawn attention. Swarms consisting of hundreds of minor quakes have been recorded over relatively short periods, particularly in areas near San Ramon. These clusters do not necessarily signal that a major earthquake is imminent, but they do indicate ongoing adjustments within the fault system. Each small movement reflects a redistribution of stress, though not always in a way that reduces overall risk. Estimates suggest that the probability of the Calaveras fault producing a magnitude 6.7 or larger earthquake within the next few decades is significant. When considered alongside other faults in the Bay Area, the broader regional risk becomes even more pronounced. The interconnected nature of these faults means that activity on one can influence conditions on another. Of particular interest is the relationship between the Calaveras fault and the nearby Hayward fault. Geological studies indicate that these faults may be linked at depth, forming a continuous structure capable of rupturing together under certain conditions. Such a combined event could produce an earthquake with a magnitude exceeding 7, amplifying its impact across densely populated areas. Although the Calaveras fault passes through regions that are less densely populated than some neighboring faults, it still directly affects hundreds of thousands of residents. Beyond those living directly above or near the fault, the broader Bay Area is interconnected through infrastructure that crosses multiple fault lines. Highways, rail systems, pipelines, and electrical networks all intersect with this shifting ground. The implications extend beyond immediate structural damage. A significant earthquake along the fault could disrupt transportation corridors, interrupt power distribution, and affect water supply systems. Even areas located miles away could experience secondary impacts due to the interconnected nature of urban systems. Despite these risks, the region has taken extensive measures to improve resilience. Building codes introduced in the early 20th century and continuously updated since then have significantly enhanced the ability of structures to withstand seismic forces. Modern engineering techniques aim to absorb and dissipate energy, reducing the likelihood of catastrophic collapse. However, no amount of preparation can eliminate risk entirely. The Calaveras fault remains an active and evolving feature of the landscape, shaped by forces operating far beneath the surface. Its quiet, creeping motion offers a glimpse into the complex mechanics of Earth's crust, where movement does not always announce itself through dramatic events. The contrast between its steady surface displacement and its potential for sudden earthquakes is what keeps attention focused on this fault. It behaves in ways that challenge simple assumptions about how faults operate. It releases energy, yet not always enough. It moves, yet not uniformly. It appears stable, yet retains the capacity for disruption. As activity continues along its length, each subtle shift contributes to a larger pattern that is still being understood. The ground beneath these communities is not static, but part of a dynamic system that evolves over time. Measurements, observations, and historical records provide pieces of the puzzle, but they do not offer complete certainty. Beneath the same stretch of land, where gradual displacement continues to reshape streets and structures, the deeper sections of the Calaveras fault remain under a different set of conditions, where motion is far less forgiving and far less predictable. While the upper layers may slip quietly through creeping behavior, the lower portions are subjected to increasing pressure as tectonic forces persist without interruption. Over time, this imbalance between steady surface movement and locked deeper zones creates a complex pattern of strain accumulation that does not resolve itself evenly. The mechanics behind this imbalance are tied to depth, temperature, and pressure. At shallow levels, the presence of serpentinite and elevated pore fluid pressure reduces friction, allowing gradual displacement. But as depth increases, temperatures rise and rock properties change. Materials that behave in a more ductile manner near the surface can transition into stronger, more rigid forms capable of resisting motion. These deeper sections effectively act as barriers, preventing the continuous release of stress and allowing energy to build over extended periods. This stored energy does not disappear. It accumulates in the form of elastic strain, gradually deforming the surrounding rock. When the stress exceeds the strength of the locked section, the result is a sudden rupture that propagates along the fault. This process is what produces earthquakes, and it explains why a fault capable of creeping can still generate significant seismic events. The length of the Calaveras fault plays a critical role in determining the scale of such events. Extending for approximately 76 miles, or about 122 kilometers, it has the physical capacity to produce earthquakes that range from moderate to strong. A full rupture along its entire length could generate an event approaching magnitude 7.4, while more localized ruptures are likely to fall within the range of 6.5 to 7.0. Even at the lower end of this range, the impact on surrounding communities could be substantial. The distribution of stress along the fault is not uniform, and this unevenness introduces another layer of uncertainty. Some segments may be releasing energy steadily through creep, while others remain locked and increasingly strained. This patchwork of behavior creates conditions where certain sections could fail independently or in sequence. In some scenarios, rupture in one segment could transfer stress to another, increasing the likelihood of additional movement. Attention has increasingly focused on the potential interaction between the Calaveras fault and the Hayward fault. Geological evidence suggests that these two faults may be connected beneath the surface, forming a continuous structure that extends through the eastern portion of the San Francisco Bay area. If a rupture were to propagate from one fault to the other, the combined length of the break could produce a significantly larger earthquake than either fault might generate alone. Such a scenario would have far-reaching implications. The Hayward Fault runs directly beneath densely populated urban areas, including cities with critical infrastructure and high population density. A combined rupture involving both faults could affect millions of residents, amplifying the scale of damage and disruption. The possibility of this kind of linked event, while not certain, is one of the reasons the region remains under close observation. Patterns of recent seismic activity provide additional insight into the ongoing adjustments within the fault system. Swarms of smaller earthquakes have been recorded in areas along the Calaveras fault, particularly in regions near San Ramon and Mount Hamilton. These clusters can consist of dozens or even hundreds of minor events occurring over days or weeks. While individually too small to cause damage, they reflect shifts in stress distribution within the crust. Such swarms are often interpreted as signs of localized movement, where small adjustments relieve pressure in specific areas. However, they do not necessarily indicate that the overall system is becoming less hazardous. In some cases, they may even redistribute stress in ways that increase pressure elsewhere along the fault. This dual nature makes them difficult to interpret with certainty. The historical record adds further context to these observations. Over the past century and a half, the Calaveras fault has produced several earthquakes of magnitude 6 or greater, with an average interval of a few decades between significant events. This pattern suggests a recurring cycle of stress accumulation and release, though not one that follows a precise or predictable timetable. Modern monitoring systems have improved the ability to detect and analyze activity along the fault. Networks of seismometers, GPS instruments, and satellite-based measurements provide continuous data on ground movement and seismic behavior. These tools allow for detailed tracking of creep rates, fault slip, and microseismic activity, offering a clearer picture of how the fault is evolving over time. Despite these advances, forecasting the exact timing and magnitude of future earthquakes remains beyond current capabilities. The complexity of the fault system, combined with the variability of geological conditions, limits the precision of predictions. Probabilities can be estimated over long periods, but short-term forecasts remain uncertain. Current projections indicate a notable likelihood that the Calaveras fault could produce a magnitude 6.7 or larger earthquake within the coming decades. When combined with the broader network of faults in the region, the probability of a major earthquake affecting the San Francisco Bay Area rises significantly. These estimates are based on historical patterns, geological data, and statistical modeling, all of which point to the inevitability of future seismic activity. Infrastructure throughout the region reflects both awareness of this risk and the challenges it presents. Major transportation routes, including highways and rail lines, cross the fault at multiple points. Pipelines carrying water, natural gas, and other resources intersect with shifting ground. Electrical transmission lines and communication networks are similarly exposed. In the event of a significant earthquake, disruptions to these systems could extend far beyond the immediate area of the rupture. Urban development patterns also influence the potential impact of seismic events. While some areas along the Calaveras fault are less densely populated than those along the Hayward fault, they are still home to hundreds of thousands of people. Residential neighborhoods, commercial centers, and industrial facilities all exist within reach of the fault's influence. The interconnected nature of the Bay Area means that damage in one location can have cascading effects across the region. Engineering advancements have played a crucial role in reducing vulnerability. Buildings constructed under modern seismic codes are designed to withstand shaking by incorporating flexibility and energy dissipation features. Retrofitting older structures has further improved resilience, particularly in critical facilities such as hospitals, schools, and emergency response centers. These measures do not eliminate damage, but aim to prevent catastrophic failure and loss of life. Preparedness extends beyond construction practices. Emergency response planning, public awareness campaigns, and early warning systems all contribute to reducing risk. Systems capable of detecting the initial waves of an earthquake can provide seconds of warning before stronger shaking arrives, allowing for automated responses such as stopping trains or shutting down industrial processes. Even with these measures in place, the underlying reality remains unchanged. The Calaveras Fault is an active component of a larger tectonic system that continues to evolve. Its creeping motion, while reducing stress in some areas, does not prevent the buildup of energy at depth. Its history of moderate earthquakes demonstrates its capacity for sudden movement. Its potential connection to neighboring faults introduces the possibility of larger, more complex events. Each subtle shift observed at the surface is part of a broader process unfolding beneath the ground. The displacement of a sidewalk or the gradual misalignment of a roadway reflects forces operating miles below, where pressure and friction interact in ways that are not directly visible. These surface indicators provide valuable clues, but they represent only a fraction of the full picture. Understanding this fault requires recognizing both its quiet and its forceful aspects. It is neither entirely benign nor constantly destructive. It exists in a state of ongoing adjustment, where periods of relative calm are interspersed with moments of release. This dual nature is what sustains continued attention, as it challenges assumptions about how faults behave and how risk should be assessed. Across the communities that lie along its path, the evidence of movement is already present, etched into the built environment through years of gradual displacement. These changes serve as a reminder that the ground itself is not fixed, even when it appears stable. The forces shaping it operate on timescales that extend beyond immediate perception, yet their effects accumulate in ways that cannot be ignored. As monitoring continues and data accumulates, the picture of the Calaveras Fault becomes clearer in some respects and more complex in others. Each measurement adds detail, but also highlights the variability inherent in natural systems. The challenge lies not only in understanding how the fault behaves, but in anticipating how its behavior might change under evolving conditions. The stakes are defined not just by the magnitude of potential earthquakes, but by the scale of the communities and infrastructure that intersect with the fault. The interaction between natural processes and human development creates a dynamic environment where risk is constantly being reshaped. This interaction underscores the importance of continued observation, preparation, and adaptation. The movement beneath the surface does not pause, and neither does the need to account for it. The Calaveras Fault remains a defining feature of the region's geology, one that continues to influence both the physical landscape and the planning decisions made above it. If you found this deep dive informative and valuable, make sure to like, share, and subscribe for more content like this. Do not forget to tap that hype icon to help this reach a wider audience.